In a basement lab in Birmingham, England, a physicist built a universe, a real one, smaller than a grain of rice. Inside it, he watched something that no one had ever directly witnessed before. Time itself, being born out of nothing at all. And he pulled it off with a trick that sounds like cheating. He deliberately ignored one half of his own experiment. Nobody caught him. Nobody objected. Because ignoring half of everything, it turns out, might be exactly what the universe does to us. That universe was a cloud of 24,000 atoms, chilled down to a few billionths of a degree above absolute zero. Almost nothing found in nature is that cold. At this temperature, atoms nearly stop moving altogether. And then, something strange happens. They blur together, losing their individual identities and begin behaving as one single, unified quantum object. Physicists call this state of matter a Bose-Einstein condensate. Professor Giovanni Barantini calls his version something grander, a miniature universe, sealed off completely from the outside world. This tiny cosmos contained no clocks, no timers, nothing external to measure change against. Which was exactly the point, because the real universe, the one you live in, has precisely the same problem. There is nothing outside our universe. No cosmic wall clock, no referee with a stopwatch, no external anything to tick. So if nothing outside the universe can tick, where does time actually come from? That question has haunted physics for 60 years. To see why, rewind 3.5 centuries, to the man who defined time for the modern world. Isaac Newton pictured time as a river, absolute and universal, flowing at exactly the same rate for everyone, everywhere, forever. In Newton's physics, time is the stage. Events perform on top of it, but nothing any event does can touch the stage itself. Then Albert Einstein came along and tore that comfortable picture apart, not once, but twice, within a single decade. In relativity, time bends, stretches, and slows down depending on gravity and on how fast you happen to be moving. A clock near a massive planet ticks slower than one in empty space. Time became flexible, but it was still real, still fundamental. The real crisis arrived when physicists tried merging Einstein's relativity with quantum mechanics, the physics governing atoms and particles. Those two theories each rule their own domain perfectly. Force them together, and something extraordinary falls out of the mathematics. Physicists John Wheeler and Bryce DeWitt spent the 1960s trying to write quantum rules for gravity itself. In 1967, DeWitt formalized the effort into a single master equation meant to describe the entire universe at once. It's called the Wheeler-DeWitt equation, and it contains something genuinely shocking. There is no time variable in it. This wasn't a typo or an oversight. The mathematics itself insists the total energy state of the whole universe never changes. Taken literally, the equation says the universe as a whole is stationary. Nothing evolves. The cosmos is frozen solid. And yet you remember yesterday. You plan for tomorrow. Stars burn out. Coffee goes cold. Something is clearly happening. That contradiction has an official name, the problem of time, and it sits at the very heart of quantum gravity. Every attempt to unify physics runs into it. You cannot describe the whole of reality, it seems, without losing time itself. For over a decade, the problem looked completely unsolvable, a crack running through the very foundations of physics. Then, in 1983, two physicists quietly proposed an escape route, an idea that bordered on heresy. Don Page and William Wooders published their proposal under a title that reads like a riddle: Evolution without evolution. Their claim: maybe time isn't fundamental to reality at all. Maybe time is something the universe makes from the inside. Here's the idea. The whole universe really is frozen, exactly as the master equation insists. But you are not standing outside it. You are inside. And inside, parts of the universe are quantum entangled with other parts, their states permanently linked together. Entanglement means two systems share one description. Learn something about one, and you instantly know something about the other. So pick one piece of the universe, any piece at all, and simply agree to call that chosen piece a clock. Now compare everything else against it. Relative to that clock, the rest of the universe changes. Correlations play the role of time. Seen from outside, a frozen, motionless block. Experienced from inside, a flowing history, complete with past, present, and future. Time, in this picture, becomes a matter of perspective, relational, not absolute. Not a river at all, but a relationship. It was beautiful. It was radical. And for 3 full decades, it remained nothing more than mathematics on paper. The idea sat in journals, admired and untouched, waiting for an experiment that could actually reach it. Eventually, researchers led by Ekaterina Moreva managed to test one small piece of it using just 2 particles of light. 2 photons were entangled together, and one of them was assigned the role of the clock for its partner. Reading the experiment through the clock photon, from the inside, the partner photon visibly evolved and changed. But viewed from the outside, ignoring the clock, the very same pair of photons sat perfectly, utterly still. One experiment, 2 completely different realities, moving inside, frozen outside, exactly as Page and Wooders had predicted. It was a landmark result. But let's be honest, 2 photons, however elegantly arranged, do not make a universe. A real test needed a closed system with many parts. Expansion, collapse, disorder. A genuine cosmos in miniature. Relational time had never been tested directly in a system like that. No one had ever built one. To genuinely test whether time could be born, somebody was going to have to build themselves a cosmos. Barantini's inspiration arrived while he was watching his son play with building toys, assembling little worlds piece by piece. His lab, he realized, plays the very same game with far more expensive toys, building small, controllable samples of reality. So he built one, 24,000 rubidium atoms trapped in place by magnets and laser light, cooled to near absolute stillness. The trap held the cloud hermetically sealed, a self-contained quantum system with no connection to the world outside. Then came the crucial move. 2 laser beams sliced a thin barrier straight through the cloud, dividing the tiny cosmos in 2. One half of it he watched constantly, measuring everything that happened inside. He named that region the bright sector. The other half he simply refused to ever observe. No measurements, no glances. He called that hidden region the dark sector. And that is the half of his own experiment he deliberately ignored. The cheat that wasn't a cheat at all. Atoms could slip back and forth across the barrier, but the system as a whole stayed perfectly sealed from the outside world. Just like the real universe, things happen inside it, but there is no outside vantage point and no external clock. And then the bright half of this miniature cosmos began to breathe, expanding and contracting, over and over, like a slow heartbeat. Cycles of growth and collapse, echoing cosmology's grandest scenarios, a big bang followed by a big crunch, repeating in miniature. Here is where time appeared. As atoms crossed the barrier, the spread of the particles inside the bright sector kept changing. Spread is what physicists call entropy, roughly how disordered or mixed up a collection of things has become. A tidy room has low entropy. A messy one has high entropy. And messes, famously, tend to grow rather than shrink. In the mini-universe, that spread became the clock itself. Whenever it changed, the system was moving forward in time. No stopwatch, no oscillator, no ticking, anything. Just the changing arrangement of atoms, defining before and after all by itself. And this newborn internal time did genuinely strange things. It sped up, slowed down, and even stopped entirely. Time was speeding up, or slowing down, or even stopping, Barantini said, depending entirely on what the system was doing. To prove this was physics and not just a metaphor, he rewrote quantum mechanics' central law, the Schrödinger equation, using entropic time. The Schrödinger equation normally predicts how a quantum system changes from moment to external moment. His version used internal moments instead. He solved the rewritten equation numerically and compared its predictions against the actual measured behavior of his condensate cycle after cycle. They matched closely, right down to the changing width of the bright sector as the miniature universe expanded and contracted. The agreement surprised even Barantini himself. Things in experimental physics, he noted, rarely come together quite so neatly. And hidden inside the setup was a bonus answer to one of the oldest riddles of all, time's direction. Nothing in the fundamental laws of physics forbids time from running backward, yet eggs never unscramble, and memories only point one way. Physicists call this one-way flow the arrow of time, and where it comes from has never been settled. The mini-universe offers a suspect. The arrow, it suggests, appears when an observer gives up information. When Barantini chose never to look at the dark sector, he permanently surrendered his knowledge of that half of reality. That sacrifice, that deliberate ignorance, is precisely what gave his miniature universe a forward direction at all. Both time and its arrow, in other words, may flow from the very same source. What an observer cannot or will not see. Which turns the cheat from the very beginning of this story completely on its head. The trick was the discovery. The Danfrit perfect, my delights to Epibeat stud again. It may be the same thing the universe quietly does to every one of us. We are all inside, entangled with everything, blind to most of it, and perhaps that blindness is why anything flows at all. Published in Physical Review Research in June 2026, this stands as a first, controlled experimental evidence of emergent time. Careful physicists will note the limits. It's a proof of concept in an analog system, not a photograph of quantum gravity itself. But proofs of concept are how revolutions start. The same cold atom toolkit could now simulate black holes, early universes, even a big crunch. So the next time you glance at your watch, consider what it might really be measuring. Not a river flowing past you, but relationships. Countless quantum threads between you and everything else, weaving the sensation you call the passage of time. And physicists have already made time inside quantum systems appear to run backward. That story is next.